Boom! What up, mathletes? Whoop. All right, let's do this today. Classify each polygon by the number of sides. Say whether it's convex or concave, regular or not regular. Ready, set. Oh, and then down here, sketch each polygon. So, ready, set, go. Okay, pause if you need more time. Let's do this. So I'm just going to actually go ahead and hit the show answer button so you guys can see some examples. This is a quadrilateral. It's 4 sides. Quad means 4, lateral sided. And it's convex and regular. Regular means the sides are the same length. They're congruent. Concave, or excuse me, it's convex, not concave. And convex means that it's straight or bowed out. Concave means it's going in. Okay? So this is a pentagon. It is not regular. These sides are clearly different in length, and it is concave in. This is a hexagon. It's 1, 2, 3, 4, 5, 6-sided. It is convex because they are straight, but it is also not regular because these sides are of different lengths. A regular polygon, well, this is just a pentagon, a regular pentagon right here. It's convex. Sides are same length. Concave octagon means 8-sided, so 1, 2, 3, 4, 5, 6, 7, 8. And it could even be regular. I don't know. I can't really tell. It looks like these sides are smaller than these sides, though, so probably not. But it is concave in that it goes inside. And then last is a triangle that is not regular. In other words, these sides are of different lengths. Or at least one side is of different length, but all three appear to be. Okay, let's move on from the warm-up. Let's do this. Y'all ready for this today? It's good stuff. All right, basically what we said, so I'm going to read this to you. Let me go ahead and zoom in, though. You don't necessarily need to see the whole picture. You guys can see there's a good difference in those pictures there. In a computer graphics plot, polygonal modeling is a method used to model three-dimensional objects. Polygonal models use, I know some people will be like, that's polygonal, Mr. Jim. No, it's actually pronounced polygonal. It's a polygon, but it's polygonal when, I don't know, plural is the word. Models use two-dimensional polygons to represent the surface of objects. Triangles and quadrilaterals are the most common shapes used in polygonal modeling. When fewer polygons are used in a model, the surface of the objects can look cartoon-like, kind of like this one right here. It says fewer objects. So you see the shapes are larger, so fewer assets are being used. Over here, the shapes have been broken down into smaller shapes, so it's a little less cartoony looking. Arguably, if you really do that a lot more, it'll look more and more realistic. To make objects look more realistic, computer graphic designers subdivide the polygons on a model by adding more vertices. When a polygon is subdivided, the sum of the interior angle measure is equal to the sum of the angle measures of the new polygons that have been formed. So we'll talk about that a little bit. In other words, if I break this down into multiple, so we see like a big triangle here. If I break this down into several different shapes, I can add up the angles of those shapes, and it's going to equal the sum of the whole. But let's look and find out what's going on. And that's really what we're talking about today. Boom. Wait for it. Angles of polygons. We're going to talk about a lot of angles today. Triangles, all sorts of different stuff. It's going to be fantastic. First of all, a diagonal. It's important to understand a diagonal is a segment that connects any two non-consecutive vertices within a polygon. So in other words, they can't be vertices right next to each other, right? So if I'm drawing a shape, guys, it's not going to be perfect. There's a quadrilateral. In other words, if I'm to draw a diagonal, right, I have to draw the diagonal. Consecutive vertex would be right here. I can't connect those. I'd have to draw it to a non-consecutive vertex. Okay? So the red is a diagonal. Let me get a different color. Green is not. So this is not a diagonal. That's just a side, right? The other one's an actual diagonal. Okay. All right. Write that down and let's move on. I want to get into these theorems and all these awesomeness that's going on today. Today will be the longer of the 2-day lesson, but we'll get through it. It'll be excellent. Excellent. All right, now I am going to make this a little bit smaller. So we're basically going to explore angles here. So what's we're going to do? I'm going to construct this triangle, and I'm going to make it scalene. Just means the sides are of different values. Notice the sum of the interior angles of the triangle are 180 degrees. So this is set up to measure the angles, and you're not going to see it change because it won't change. It's always 180 degrees. And how many sides are there? 3. How many triangles make up this figure? Well, it's just one triangle. So let's do this. All right. So number of sides is 3. Number of triangles is 1. The angles add up to 180. We know that. Sum of the triangles is always 180. Angles of a triangle. Let's talk about a quadrilateral. I'm going to make this over here. And it's just a 4-sided figure. It doesn't need to be square. Doesn't need to be parallelogram, any of that. It's more trapezoidal now. Oop, I'm going to leave that with the triangle. I want to take this one down here, though. Look at this. So the sum, maybe I can do that. There we go. Let's move this up out of the way. Sorry, I'm just trying to make room because I know I'm going to be doing a few of these. Okay, what is the sum of the interior angles of the quadrilateral DEFG is 360 degrees. And I'm going to draw a diagonal on this one. I'm going to connect D to F. How many triangles did I just create? Notice that there's 1 triangle, 2 triangles. What are the angles of a triangle add up to? So that's 180 degrees, that's 180 degrees, so 180 plus 180 is 360. All right, so check this out. Are you ready? There's 4 sides in a quadrilateral. I just showed by drawing the diagonal that it separates it into 2 triangles. And the sum of the interior angles measure 360 degrees, right? So the sum of, and by interior angles, just so we understand each other, that would be angle D, angle E, angle F, and angle G. Okay, now let's talk about a pentagon. So we did a 3-sided figure. Now we're going to do we did a 4-sided figure, and now we're going to do a 5-sided figure. And again, these are not regular. All regular means is that all the sides are the same. I'm making them irregular on purpose to show you that that doesn't matter. And the sum of these angles are 500 of the interior angles of a pentagon. JKLMN is 540 degrees. I'm going to go ahead and draw the diagonal LN and LJ. So now, once again, I've separated this into triangles, and I have 1, 2, 3 triangles. So we have a 5-sided figure with 3 triangles that it's made up of, and that is 540 degrees. We're almost done here. One more figure. Let's do a hexagon. Okay, it came out in almost the right spot. Okay. And again, I'm going to go ahead and draw all the diagonals here. So from R, notice I'm just picking one vertex, and I'm drawing all the possible diagonals from that vertex. Now look at this. How many triangles did I just separate this into? 1, 2, 3, 4. So it's a 6-sided figure with 4 triangles it's made up of, and that is 720 degrees. Now, and again, I can drag any of these figures around. You'll notice that that sum doesn't change because that's just what it is. Exercise 1 tells us, all right, let's get them loading up. What is the relationship between the number of triangles created by the diagonals of a polygon and the sum of the interior measures of the angle? Is there a relationship between this? Well, one triangle is 180 degrees, 2 is 360. But let's think about this. What's 2 times 180? Doesn't that equal 360? How about if it's made up of 3 triangles, what's 3 times 180? Doesn't that equal 540? And what's 4 times 180? Well, that's 720. And that makes sense because, remember, if it's made up of 1 triangle, the sum of the angles of a triangle is 180 degrees. If it's made up of 2 triangles, each of those triangles adds to 180 degrees, so 180 plus 180 would be 360. If it's made up of 3 triangles, each of them adding 280, we'd multiply times 3, and so on and so forth. So the reason why we were separating each of these shapes up here into triangles is because we're able to see that that's where that angle measure is coming from. Since the angles of a triangle all add up to 180, 2 triangles would be 360, 3 would be 540, and 4 triangles would be 720 degrees. Guess what? If you want to shape up, it'd be 900 degrees because that'd be another 180 degree triangle added. All right, so what is the relationship between them? The measure of the interior angles is equal to the number of triangles created times 180 degrees. Awesome. And then let's go to exercise 2. What does that tell us? What is the relationship between the number of sides and the number of triangles formed? Well, if there was 3 sides, 1 was formed. 4 sides, 2 were formed. 5 sides, 3 were formed. 6 sides, 4 were formed. Does anybody notice that there's a difference of 2 each time? So in other words, if I were to put this in mathematical terms, 3 minus 2 is 1. 4 minus 2 is 2. 5 minus 2 is 3. 6 minus 2 is 4. So what does that tell me? The relationship is there are 2 fewer triangles created in each shape than sides. So the number of sides minus 2 will always get us the number of triangles in a convex polygon. Okay, exercise 3. What is the relationship between the number of sides of a polygon and the interior angle measure? Well, going by this, let's see if it's minus 2 and then times 180. So again, minus 2 gets me to 2, and then 2 times 180 is 360. 5 minus 2 is 3, times 180 is 540. So the relationship between the number of sides and the interior measure is the number of sides minus 2 times, or I should put a comma, times 180 is equal to the measure of the interior angles. And then last but not least, can we come up with an expression? Well, yeah, I could say number of sides, let n be the number of sides, n minus 2 times 180 equals of the interior angles. Look at that. What you actually watched me do was actually help come up with the theorem we're about to learn. So let's go to the next slide. And I'm going to zoom in a tad. So, we're going to talk about theorem 7.1, I believe it is. Yeah. First of all, how can you use what you already know about the triangles to determine the sum of the measures of the interior angles of polygon PQRST? Well, we're really going to skip on down to here. Theorem 7.1 is the polygon interior angle sum theorem, and it says the sum of the interior angle measures of an n-sided convex polygon is n minus 2 times 180. So in other words, if we're looking at a pentagon right here, an example would be the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D plus the measure of angle E equals 5 minus 2, which is 3, times 180, which is 540. Go ahead and write that down. Pause it if you need to. Stinking fly that's buzzing around. If you see me randomly smack out, that's what I'm trying to get. Awesome. Write this down, make sure you have the example, and let's move on. Find the measure of each interior angle of the pentagon HJKLM. Well, if it is a 5-sided polygon, I know that the sum of all these angles is going to be 5 minus 2 times 180. So step 1, find the sum. I know the sum of the measure of angle H plus J plus K plus L plus M is equal to n minus 2 times 180, which is 5 minus 2 times 180, or 540 degrees. Now, guys, I don't need you to show this every time. My goodness. And especially once you memorize some of these, you can just say, sum of the angles is 540 degrees, or a pentagon angles equals 540 degrees. You can just put that in there. We don't need to keep reinventing the wheel. But how does that help us? Because now we can set up an equation. And what is the equation I can set up? I can set up, all right, 2x plus 142 plus 2x plus 3x plus 14 plus 3x plus 14. What does that all equal? Should all equal, sorry, I'm taking up a lot of room, 540 degrees. All I did was add up all these interior angles. So let's combine like terms. Use a different color, blue. 2x plus 2x plus 3x plus 3x. We can combine all those, and that's going to be 2x plus 2x is 4x plus 3x is 7x plus 3x is 10x. So I'm going to have 10x. And then 142 plus 14 is 156 plus 14, 166, 170 plus 170. That's a terrible plus line. Plus 170 equals 540 degrees. Let's do this. Subtract 170 from both sides. I know that 10x equals 370 degrees. Divide both sides by 10. Divide by 10. And I get that x equals 37 degrees. We're not done. We just solved for x. Let's go ahead, pause this, write it down because I'm about to erase it. Now we got to solve for each one. If x equals 37 degrees, I don't want to undo that. Let's use a different color. I'm going to use red. Then I know that 2x can be 2 times 37, which equals what? 74. All right, so I know the measure of angle H is 74 degrees, and the measure of angle K is 74 degrees. So again, what do I know? measure of angle H and angle K equals 74 degrees. All right. What do I know next? Let's look at the 3x plus 14. So 3 times 37 plus 14. 3 times 37 is what? 90 plus 21. So 111. So that's going to be 111. Sorry, I didn't finish that out. Plus 14, which equals 125. 125. So I've got now that, I'll write this in a different color. Go green. The measure of angle M and angle L equals 125 degrees. Then we already are told that the measure of angle J equals 142 degrees. So let's see if that's true. I have two angles at 74 degrees, two angles at 125 degrees, and one at 142. I'm going to add this up in my calculator. Let's see. 2 times 74 plus 2 times 125 plus 142. Look at that. I don't know if you can see it real well, but that's 540 degrees, which is the angle measure of our pentagon, the interior angle measure. So this is how we find all those angles. Awesome. Let's roll on. I'm going to delete this. 3, 2, 1. A couple more examples for today before we're done. Just want to make sure you guys have examples for doing your homework. All right. Penny is building a house using a floor plan that she designed. What is the measure of angle ABC? Well, what is our task? We need to find this angle measure of ABC. Now, what kind of a shape do we have? Well, how many shapes do we have? We have, it's a 1, 2, 3, 4, 5, 6-sided figure. So we know that the sum of the interior angles is going to be 6 minus 2 times 180, which is 4 times 180, or 402 and 320, which is 720. That's 720 degrees. Here's what else we know. All these sides are the same length, which means it's a regular hexagon. So that means every one of these angles, by definition, are going to be the same. Because of that, I can just say if it's a 6-sided figure, let's divide 720 by 6 to get the measure of each individual angle. 720 divided by 6 is 120 degrees. Awesome. So I know that the measure of angle ABC equals 120 degrees. And we need to ask ourselves, is this a reasonable answer? Right? That's the thing we should be having in the back of our mind. We don't want to get some off-the-wall answer. Be like, oh, that must be it. The math said it's it. No, is it reasonable? Well, let's find out. If it's reasonable, let's see, 120. I'm saying that every single one of these 6 angles is 120 degrees. So it should be that 120 times 6 equals, let's find out, times 6 equals 720, which again is the measure of the interior angles of a hexagon, any hexagon, regular or not. So yes, this is a reasonable answer. And And we're going to stick with the measure of angle. ABC is 120 degrees. Boom. Pause if you need to. Going, gone. And last for the day, what is it? You know it's going to be a hard one, right? Got to end on that next level thinking. It's really not that hard. The measure of an interior angle of a regular polygon, so it's regular, so we know all the sides have the same measure. That's what that regular tells us, is 144 degrees. Find the number of sides in the polygon. Okay, we have some polygon. We're going to let n be the number of the sides of the polygon. So let's highlight this a little bit. I want green. We're going to let n be the number of the sides of the polygon. Because all of the sides of or angles of a regular polygon are congruent, the sum of the interior angle measure is 144 times n, right? Just like the last one, we took the 120 and multiplied it times 6 to get 720 because each of the 6 angles was the same. We're going to multiply this times whatever the number of the sides is, and that's going to get the angle measure. Here's what else I know. We know by the theorem, by the angle sum theorem, interior angle sum theorem, that n minus 2 times 180 is also equal to the sum of the interior angles. So what can I say now? Well, let's get rid of this. I can say 144 times n is equal to n minus 2 times 180, right? Now that's where we got to do some math. We're going to distribute a little bit, and we're going to do a little division. So I'm going to distribute the 180, and we get that 144n is equal to 180n minus 360. So now I'm going to go ahead and subtract 180 from both sides. 180n minus 180n. Don't worry about those negatives. They'll take care of themselves. And we'll get what? Negative 36n is equal to, that cancels out, negative 360. Let's divide both sides by negative 36. And those negatives cancel out to a positive, and I get that n is equal to what? Negative divided by negative is positive. 360 divided by 36 is 10. So I get, go ahead and pause this, copy down, I'm going to erase it, that my n equals 10. And that the polygon has 10 sides, so it is a regular decagon. That is the name of a 10-sided figure. Boom, that's it for today. Peace out.